the opposite is not always true. Right, so if it's strongly connected, then you can get between any pair of points following the arrows. Then forgetting about the arrows, that gives you an ordinary path. So that, therefore, it is always weakly connected. But my next example will show that there are graphs which are weakly connected but not strongly connected. Here's an example of such a graph. Again, 6 vertices arranged as before. Probably labeled as before. A, B, yeah, C, F, D, E. But yeah, same edges, but the arrows are different. So, yeah, the BC arrow is reversed. And that's it, right? Just one arrow is reversed, BC, with respect to the previous example. So these graphs, it's easy to check that it is weakly connected. Right, visually you can see it consists of one piece. Right, this graph is weakly connected, but not strongly connected, because B, the vertex B has only outgoing arrows, right? Therefore, there is no way to arrive to B following the arrows. Because vertex B has only outgoing edges and there is no way to get to B via a directed path starting from any other vertex. Okay. So that generalizes also easily. Whenever you see a graph and you have a vertex with only outgoing edges or a vertex with only incoming edges, they can be called sources and sinks if you think of these arrows as kind of flux lines, like electric current lines. So if you have, it's basically have one sink or one source to conclude that that graph is not strongly connected. Okay. Right. So when we discussed ordinary graphs, when they were not connected, then immediately we introduced the notion of connected components, and then we would describe more precisely, in what ways it's not connected. So it would break up into several connected components. Here, we will also introduce the notion of strongly connected components. So let G be a G graph. A directed subgraph of G is called a strongly connected component if it is strongly connected, and it cannot be contained in any larger strongly connected subgraph of G. It's very similar definition to the ordinary connectivity. You just have to add, strongly connected whenever you talk about, connectedness here. So a directed subgraph of G. So what do we mean? I remind you, subgraph is something you obtain from the original graph by removing some vertices and some edges. It can be done in many different ways. The only requirement is that whenever you remove a vertex, you have to also remove all edges ending on that vertex, right? Otherwise, it would be inconsistent. You would have some edges ending nowhere, right, at the vertex which was removed. So that's the only consistency requirement. In the case of the directed graph, right, since you decide to keep some of the edges, you immediately inherit some the arrows which were put on these edges. So you end up with a subgraph which is directed, a directed graph. Right? Okay, so that's what I mean here. So continuing with the definition, a directed subgraph of G is called a strongly connected component of G. It's called a strongly connected component of G if, let's put like two conditions. A, it is strongly connected. And B, it is not contained in any larger strongly connected subgraph of G. It is not contained in any larger strongly connected subgraph of G. G is our original G graph. So let's determine the strongly connected components in the previous example. So if you have a sink or a source, like the vertex B, then that vertex by itself forms a strongly connected component. Nothing can be added to it. So for the previous example, so firstly, we find that B, just the vertex B, without any other vertices added to it, we can call this as G1. So that's our first strongly connected component. Right? I start with it because I noticed it before, right? That was the culprit of not having strong connectedness. And next I can just pick any other vertex and see if you can travel from that vertex back and forth to any other vertex. If you can, then those two vertices together, they sit in the same connected component, right? Then you see if there's any third vertex such that you can travel to any one of those two back and forth, respecting the arrows. If yes, then you add it, and you search for the fourth vertex, right, such that you can travel to any other of the previous three vertices back and forth, right? So you can grow your connected component like that. Well, let's start with A, right? And, well, I immediately noticed that the only way to arrive to A, right, is from vertex B. But there is no way to arrive to vertex B because it's a source. So I claim then that there is no way to arrive from any other vertex except for B to A, right? But B together with A cannot be put into the same strongly connected component because I cannot travel back from A to B. There's no way to get to B at all. So A, again, by itself, forms a strongly connected component, so I call it G2. So nothing can be added to it. Okay, let's next pick up C. Okay, so I can travel from C to D, and then from D I can travel to E and then back to C. So C and D together belong to a strongly connected component. Moreover, E is in the same connected component because I can get from E to C, and from C to E I can get through D. In fact, these three vertices together, they form what is called a cycle. So if I draw it, it will look like this. It's a cycle with three vertices. D and E, right? Whenever you have any number of vertices, here it's 3, but could be 4, 5, 6, such that they form a cycle, so that they can travel, in a loop, respecting the arrow, then it's clear they all will be in the same connected component. The whole cycle will be part of your connected component, strongly connected component, right? Because I can travel as long as I need, along the cycle, visiting any other vertex, right? That allows me to visit, any pair from any vertex to any vertex, right? To go in a cycle. We should, of course, check that, we could have spotted this cycle from the start and decide, those three will be in the same connected component. But then, of course, we should check. Perhaps sometimes there are linked cycles, right? So the connected component may be larger. And so we definitely know we no need to bother about A and B, right? What about F? So I can travel from F to the cycle, and therefore I can visit from F any vertex, any of those three vertices in the cycle, but I cannot get to F because the only incoming vertex to F comes from B, and there is no way to get to B, right? So F cannot be added, therefore I stop here. That's my third strongly connected component. It's more interesting. And, well, incidentally, we'll also check that F is another vertex which by itself forms a strongly connected component, and this one I call G4. So this exhausts all the vertices. Each vertex must be sitting in some strongly connected component. Sometimes a really boring one, just this vertex sits there by itself and no other connections, but sometimes in something more interesting like cycles. And cycles can be attached together if you have a larger graph. So this graph, D graph, has 4 strongly connected components, and here they're all listed. And let's make this general. Let's write them down. Sorry. That was thoroughly charged. Okay. So let's write down the general remarks. First one is that each vertex of a directed graph, of a D graph, belongs to some strongly connected component. Each vertex of a D graph belongs to some strongly connected component. Second remark, whenever we have sinks of sources, they form strongly connected components containing just those vertices. Here's an example of the sink. These are sinks. sources. So they form strongly connected components containing just that vertex. Furthermore, as we've noticed cycles, remark 3, a group of vertices join in a cycle something like this, with arrows going like that, all belong to the same strongly connected component. Another remark I want to make, remark number 4, is that you can see already in the previous example that if you know all the strongly connected components, then if you want to put back together your original graph, you need to add more connections, right? That's because some parts were connected in one direction and not the other. So this, those connections have to be additionally put in. So that's different from the ordinary connected components, right, for which a disconnected graph could be always represented as just a union of non-overlapping directed components with no extra connections put in, right? Just put together these connected components and that's your graph. That's not the case for D graphs, they're strongly connected components. So let's write down, unlike ordinary connected components, we cannot represent a D graph, well, in general, as a disjoint union of its strongly connected components. So we can identify them, but it takes more to put the full graph back together than just knowing those strongly connected components. My last example is the World Wide Web, right? So it's an example of a very large directed graph, and it's interesting that it has a very large connected component, right? If you forget about the arrows, then about 90% of all websites, they're linked together, in one direction or the other direction. So it has a joint connected component. So about 90%. Then the rest 10% and actually form very small fragmented connected components. Right? So there's one giant one and lots of smaller ones. And it also has a giant strongly connected component, so that if you start from any other web page in that strongly connected component, and you start following the links, which is like following your directed edges, you can reach any other web page in that strongly connected component. It's smaller. It's about 25% of all web pages. It has a giant strongly connected component. It's about 25%. So these numbers, they fluctuate year upon year, right? So it's just kind of a reference average situation. So it always has this giant connected and the giant strongly connected. Right? And the giant strongly connected is always smaller. Any questions about the strong connectedness, strongly connected components? We assume that we somehow ordered all of the vertices. So we order the vertices so that in my set of vertices D, I have the vertices labeled as V1, the first vertex V2, the second one V3, and so on, this that. And then we define a matrix, the adjacency matrix to have entries. The adjacency matrix A has entries A, I, J with the same pair of labels for the row, for the column, and the entry labeled by I and J equals to the number of directed edges from V sub I to V sub J, from the first label to the second one. It equals to the number of directed edges from V sub I to V sub J. So let me work out the adjacency matrix for the following example. I'm going to draw a graph has 4 vertices. The label is V1, V2, V3, V4. Have a look. On V1, I have 2 edges between V1 and V2 with 2 different directions chosen. Another loop on V2, and I have a directed edge from V3 to V1, and 2 directed edges both from V3 to V4. And are arrows like this. So my adjacency matrix of color A will be a 4x4 matrix because I have 4 vertices. So I write for myself the labels draw from the picture what edges I have. So I have 1 from V1 to V1. I can do it row by row, right? So if starting from V1, I can get to vector itself. There's 1 directed edge from V1 to V2. There is no directed edge to V3. Put 0 here. And there is no directed edge to V4. So 1, 1, 0, 0. That's my first row. Starting from V2, there's no directed edge to V1. There's 1 loop from V2 to V2, and that's it. That's 0, 0. Starting from V3, I can get to V1 via 1 edge. And then from V3 to V2, there is nothing. There are no loops on V3. And there are 2 directed edges from V3 to V4, so I put 2 here. And starting with V4, I cannot get anywhere, right? That's the same. So I put zeros. Okay, so that's my adjacency matrix. And now notice that for directed graphs, it may happen that it is symmetric, but in general, they don't need to be symmetric matrices, right? So if you swap rows and columns, the 2 labels, you might get a different entry. No? Then for T graphs, the adjacency matrices need not be symmetric. That is, in general, Aij is not equal to Aj. Okay, so what's the use of it? Again, we can use these adjacency matrices to count, and this, and now we can count numbers of directed paths, paths which respect the arrows and which have a given length. So formulate it as a theorem, and then we'll work through an example. Theorem for a T graph G with the adjacency matrix A. So A is the number of directed paths of length m. M is some integer. I want to keep it different from n because n I use for the number of vertices. From Vi to Vj is given by the following matrix element. So I'm supposed to multiply the adjacency matrix by itself, taking m copies, and therefore doing m minus 1 multiplication. And then I'm supposed to take one entry with the indices ij from that matrix. All right. So let's do an example. Example. Find the number of directed paths of length 2 from A to B one has only 3 vertices, A, B, and C, but it has many directed edges. I'm just drawing them. And there's a couple of loops. On B and on C. So the first thing we need to begin to construct the adjacency matrix. So it will be a 3 by 3 matrix, and I'll use the given labels A, B, and C with alphabetic order, and exactly as I did in the previous example, I read off the entries. In this case, there's 0, 2, 1, 1, 1, 0, and 0, 2, 1. And to answer the first question, which relates to paths of length 2, I calculate the square of my adjacency matrix. So I write 2 copies, 0, 2, 1, 1, 1, 0, 0, 2, 1, 0, 2, 1, 1, 1, 0, 0, 2, 1. And I'm skipping the steps here, right? Exactly the same as we did for ordinary graphs, right? For any matrix multiplication. And you find that the entries are 2, 4, 1, 1, 3, 1, 2, 4, 1 again. So you see this didn't come out symmetric. So in general, the squares also are not symmetric. So you cannot, you have to calculate each entry, and you cannot rely on any symmetry. So once I did that, I find the relevant entry. So it's from A. So that means it's in the first row. Again, the row labels are the labels for the from vertices. And to B, that means it's in the second column. So it's this entry, which is 4. So there are 4 directed paths of length 2 from A to B. And to answer the second question, I need to calculate A cubed, right? Because it's about the path of length 3. And I have already calculated A squared. So you can write A cubed as A squared times A on the right or times A on the left. That doesn't matter which way. So I'll choose on the right. And therefore, I have to take that matrix with the entries 2, 4, 1, 1, 3, 1, 2, 4, 1, previously calculated. And right next to it, one other copy of the matrix A, which we wrote above, 0, 2, 1, 1, 1, 0, 0, 2, 1. And this time we don't need to calculate all entries, right? We only need 1 to answer the question. So from C to B, that means it's going to be in the 3rd row and the 2nd column. So we only need these entries, and we don't care about the rest of them. So let's do the arithmetic separately. Right, so it's in the 3rd row, so therefore I single out the 3rd row in the first matrix and the 2nd column in the 2nd matrix. So I get 2 times 2 plus 4 times 1 plus 1 times 2. And that gives me 10. So 10 stands there, and 10 is the answer to the second question. Right? It remains to write down the final answer. So there are 10 directed paths of length full. Oh, okay.